Okay, so we've been pretty heavy on the concepts of statistics in the last couple of videos. So this is some lighter fare. I'm going to talk about some triumphs and failure of statistics and science. So we can look a little bit at the history. The history is actually quite interesting. And there are pitfalls. So everything that I taught you until now is actually really good stuff. If we stop the course right now, you would definitely be useful members of society if you were ever to apply statistics. But going beyond this point, it becomes dangerous. So it's a good place for me to throw in some caveats of what not to do with statistics and science. Okay, so the original development of statistics, as we covered it in the course so far, this was actually done by 4 British scientists that were about 20 years apart. So one came after another. They all knew each other, they all worked with each other, and collectively they worked this out over a period of about 100 years from around 1850 to 1950. So I include Charles Darwin as an honorary member to this list, 1809, then Francis Galton, 1822, Karl Pearson, 1857, William Gosset, which we already mentioned, is 1876, and then Ronald Fischer, 1890 to 1962. So he finished the job. So it's definitely not a complete history of statistics. So there were certainly earlier mathematicians and astronomers like Gauss and Laplace who came up with probability theory and normal distributions. But I would not call them statisticians, and certainly not applied statisticians. So what inspired that push was actually the theory of evolution by Charles Darwin. And Francis Galton was his younger cousin, and he was fascinated by Charles Darwin's work. So his life goal was to explain the theory of evolution in a more quantitative and mathematical way, right? So Charles Darwin's work is qualitative. If you read his book, it's written like a novel, right? There's no mathematical formulas in it. So Francis Galton, he was a very talented mathematician. He actually looks almost the same, eh? You can definitely see the family resemblance there. Anyway, he coined the term regression, although he actually got that wrong. But he observed an interesting thing. He tried to quantify the concept of heredity. So if you take 2 parents that are dissimilar and they have offspring, they always are intermediate between the two. And so the offspring regresses toward the mean. And what that means, from his point of view, for the theory of evolution, is that there are some flaws. So you're losing diversity every generation. But this does not happen, and he couldn't figure out why. But those were the problems that they were struggling with at the time. He also investigated natural selection in picking the top end of a normal distribution, and he actually came up with a metric of standard deviations to express how far those selected individuals are away from the average. And he really was a polymath. He invented fingerprinting, so he was really the original biometrician and statistician. Now, his protege was Karl Pearson. So he actually got the correlation coefficient right, which was named after him. He became the foremost mathematician. They co-founded the journal Biometrica, which is the oldest statistics journal that still exists today. He was actually approached by William Gosset. So William Gosset, he had some natural science education, but he was not a mathematician. And if you think about it, so the t-test that he developed, that we covered, that does have a number of non-trivial problems. So one of them is, in R, we have this p norm and pt function, but those functions are actually not trivial. You start with a normal distribution, which is not a trivial formula in the first place, and then you have to integrate areas under the curve for this. And in case of t-distribution, that also depends on the number of samples, so they all have different shapes. So not an easy problem. And so he got help out of Pearson's lab. He spent some time in it. Then also at the time where William Gosset developed the first statistical test, Ronald Fischer came on the scene, and he was the youngest. He was the up-and-coming genius. He was slated to replace Pearson. So they were actually rivals. So he was only 25 when he was also approached by William Gosset. He knew to ask the right people. And so Fischer actually gave Gosset a key hint to work with degrees of freedom rather than n. So that to get those unbiased estimates of the t-distributions, you have to divide by n minus 1. And so that was something that was a major contribution to make that work of William Gosset successful. So Ronald Fischer went on to actually be the next Darwin. He ultimately explained how heredity works, how evolution works in mathematical terms. The F statistic is named after him, so that's the F test that's used in analysis of variance, which we cover later. So he was really the brains. He also recognized that that idea of statistical testing by William Gosset, that was a big deal. Pearson did not see that. At some point, Fischer wrote, Gosset had effected a logical revolution. So he acknowledged, even though he contributed a key piece to this, he always acknowledged Gosset for this contribution. And I told you that Gosset wasn't allowed to publish, but Pearson was actually the chief editor of Biometrica at the time, and they convinced him to get it out under a pseudonym. So it's known as a student's t-test. Student is a pseudonym under which this was published. You still refer to this as a student's t-test. So William Gosset is not attached to anything in statistics, although he was really the one who had effected that logical revolution. Because, if you think about it, that reverse reasoning, that you can make inferences on the unknown population mean that's in a black box, that's not a trivial insight. And so Ronald Fischer, I like him for recognizing that there was an idea that was bigger than himself. And it truly was an immense contribution. It supercharged science and the Industrial Revolution at the time, starting with agriculture, right? So understanding how evolution works and how natural selection works also lets you do quantitative genetics and crop breeding in incredible efficiency. So right after Fischer, the Green Revolution or the Agricultural Revolution took place. So at the time, nobody could imagine that the world could feed 10 billion people. That would be unthinkable without these advances. Anything in industrial design, quality control, statistics is pervasive, right? So if you have a light bulb and it says 20,000 hours lifespan, there's a statistical statement behind this. Somebody calculated that with 95% certainty, I get at least an hours out of any individual light bulb. Meteorology, forecasting is all probability based. You get your probability of precipitation for Wednesday from testing of statistical statements. Medicine, epidemiology, I already gave you examples for that. Forensics, all probability based. Mining and exploration. These are almost fields that do nothing except statistics. Engineering, it's also a big part of reliability engineering, making sure that materials withstand certain stresses. These are complex problems, all approached with statistics. Signal processing, so noisy signals in your Wi-Fi and cell phone networks. This is all statistics based. So it's pervasive in science. It's been an extremely successful concept with innumerable applications in every field. So I think Gosset's idea comes close to one of the biggest ideas in science ever. But things have also gone wrong. So what you've learned so far, that idea around the one sample t-test and confidence intervals, this is really an unqualified triumph. But starting with 2 samples or more, things become a double-edged sword. And I'm just throwing a number out, but I think possibly something like 80% of statistics and science is total nonsense. Not where it matters. If you're a researcher in epidemiology or reliability engineering, you get your statistics right or there are consequences. But in many fields, that is not the case. And there are a number of pitfalls that are extremely common. And so my job as an educator really is to make you avoid those. So there are a couple of pitfalls. I think these are the 3 biggest ones here. The first one is actually a quote from Fischer. himself. The value of p equals 0.05, corresponding to about 2 standard errors, is convenient as a limit to judge significance. So he did say that, and it really is convenient. I think that's true. I'm actually also going to use that, and I will talk about that p-value to say, okay, oh, this one was significant, another one was not. But as soon as you put statistical tests into context of the real world, this number is not relevant. So that is one thing you have to keep in mind. And most people don't know that, or most people ignore it, because it is actually rather inconvenient to figure out what the p-value actually should be. So that's a difficult thing to do. The second pitfall is if p is larger than 0.05, then there's no difference. That is also false. And then the last one is a statistical hypothesis. So there is a difference or no difference is a hypothesis, but that's also not true. So one of the easiest ways to see what's wrong with this is just redo our little simulation in R, and I draw some conclusions from my tests, and then you can see if you agree or if you object. So let's go back to our example that we are very familiar with by now. That's my 100,000 trees in the landscape here with a mean of 15 and a standard deviation of 3. So I'm going to generate my population here and look at it. That's very nice. And so now let's create a second population. Let's say these are the pine trees and those are the spruce trees from one of the first experiments that I showed you. So now the mean is definitely not 15, it's over here. So maybe the spruce grow a little bit faster in that particular ecoregion. So now my question is, which one is better? And I'm going to go out and sample 10 trees. So n is set to 10, so I'm now sampling 10, and I'm going to run my t-test. That's a bit of a disappointment, so there's no significant difference. All right, maybe I got unlucky here. Let's try this again. I'm going to go and sample this again. 0.93, so definitely not significant. But what the heck, there is a difference. I know it. I see it here. So this is my one population, mean of 15. And my other population, mean of 16. Yet, if I run this t-test, it says there's no difference. So 0.998, it doesn't get any less significant than that. So what the heck, So clearly the conclusion that if I don't get a small p-value, that there is no difference, that's totally wrong, right? And I know that in advance. I actually know it for the true populations in the foothills forests of Alberta. I know that if I were to measure all the spruce and if I measure all the pine, these would not be the same number. There will be a difference for sure. I don't know how big the difference is, but I can guarantee you that there is a difference. So that is actually not a sensible question to ask. So if I do a test like this, it would give me a sensible answer. Now let's see what happens if we actually increase the sample size a little, because this gives me a little bit more statistical power and a little bit more certainty about my means. And look at this. So I'm actually getting close to, there. Now it's significant. So we have just created a significant result. Now it's not significant anymore. That's disappointing. Now it's significant again. So that's great. That's even better, 0.03 here. Now it's not significant anymore. So it's really a disappointment. But if I were to increase this to 1,000, let's see if we have better luck. Wow, 2.2 minus 16, so 16 zeros. Whoa, 10 zeros. Okay. So that's probably the most significant work I've ever done in my life. So significance really means nothing. It means nothing in terms of application. So this is simply a function of your sample size. And it doesn't tell you anything about the difference. Now the difference that I have here, let's see, that would be 1/15. So 6%. So one species would be 6% better than another. So if I were a forestry company, that may or may not be actually significant. If I'm a lumber producer, I may be more interested in wood quality than in growth rates. 6% different in yield probably not a big deal. But if I'm a pulp mill company, that may be quite a different story. So 6% gain, that could be the difference between barely breaking even and making all your shareholders fabulously rich. For them, it would be a very significant result. So that kind of significance in the real world has nothing to do with the statistical significance. And in this case, whether I get a significant result or not means basically nothing. It's just reflection of the sampling size. So I asked the wrong question in the first place. So there are actually multiple levels of confusion about the p-value. So the first is that the p-value has nothing to do with the scientific or practical relevance of your research. It's just an estimate of confidence in a particular statistical statement that's actually not very well behaved. You've seen those p-values jump around quite a bit. Nothing like the reliability of inferences from confidence intervals, right? So those were rock solid. And the second issue is what's the appropriate alpha level? Where should you judge significance for a particular application? So in the previous example, planting spruce versus pine, if there are no big costs involved, maybe being 80% sure that spruce gives you a 5% gain or more, that's perfect. A p-value of 0.2 is fine. And in other cases, you might want to be 99.9999% sure about something when you perhaps jump out of an airplane with a parachute on. And if your takeaway from a big p-value is that there's no difference, you're also on the absolutely wrong track. And then the last one here, statistical hypothesis is a hypothesis. That is also a terrible misunderstanding that has been introduced by that statistical revolution. So if you look it up in Wikipedia, it says, a hypothesis, plural hypotheses, is a proposed explanation for a phenomenon. So that's the definition of a hypothesis. So you observe something and you wonder, how does that work? And you come up with an explanation that explains that phenomena. So that's a hypothesis. And the scientific method requires that you can test it. So you should come up with an explanation that can be tested. So that is the holy grail of science. If you follow this scientific methodology, it's very effective. So people know that. That's why everybody wants to see, can you state a hypothesis that can be tested? So if you say, oh, sure, yes, I can, and you give a statistical hypothesis that spruce and pine are different or not different, that has nothing to do with this, right? So that's not an explanation of any kind. So getting all of this wrong and falling into every single of these three pitfalls, that is actually not an uncommon failure. So the first one is probably the least problematic. If you're doing applied research, you often don't have a scientific hypothesis that guides your research, so you're not asking how things work, and you're just quantifying specific effects. So in that case, you don't need a scientific hypothesis. But if your research has the ambition to actually contribute knowledge to how things work in your field, what general principles are, and your research is guided by a trivial statistical hypothesis that you know to be false a priori, you're not going anywhere, right? So in that case, this is a showstopper. You just can't generate any new knowledge that way. Then the next pitfall that actually everybody falls into is that you do a test that actually has no value. So you don't think about a statistical statement that has value. You're just testing whether one is different from the other. So you're not testing for relevant effect sizes, but you're just asking, is this different from something else? So you're screwed. And then the third one is, whatever the result of your trivial test that has no value, you then proceed to interpret it incorrectly. So basically, if you don't get a p-value that's significant, in quotation, you say there's no difference. And if you do get a nice, significant result, you then proceed and publish it and say, oh, this is a significant contribution to science. And everybody will clap. You will get your papers out. You will get dollars. You will get promotions. And people have ridiculed these kind of studies for decades. So this is a paper with a particularly nice and sarcastic title. And there are dozens or even hundreds of those papers. This one here is because many of you work in wildlife management, so that's one example that may be worth reading for you. So I put a URL shortcut here, and they come out every year, right? So this one is from last year, out of Nature. That's the shortcut that brings you there. This is actually also a really good paper. Valentin Arnheim, Sander Greenland, Blake Shane, and more than 800 signatories call for an end to hype claims and dismissal of possibly crucial effects. So it's a problem that has been around since Gosset and Fischer invented the thing in the 1950s. And so my guess is it's not going to go away. So you'll have to live with this type of misinformation. And it's not that the studies are not valuable, just the statistical analysis that they do and the conclusions they draw, those are wrong. So you have to keep that in mind when reading scientific literature. What you have learned so far in this course actually allows you to cut through the bullshit. You understand what statistical test makes sense. So you do have to look at the figures and at the data that is presented in tables and make up your own mind. So the statistical tests often don't help you, and you have to draw your conclusions a little bit more intuitively without that powerful help that statistics could provide, because what they've done is actually not right and the conclusions they have drawn are wrong. So both in terms of hype claims and in terms of dismissal of important effects. And obviously you don't want to contribute to these kind of studies yourself. So keep that in mind when developing your own projects. So I'm unlikely to clap. And you have the knowledge to formulate proper statistical statements like we've discussed in the earlier videos.